Frequency responses have roughly the same level of importance as differential equations had in the time domain. As with differential equations, we'd like to be able to check our frequency responses to see if it makes sense before we use it to base engineering decisions on. This video talks about how to perform those kinds of checks. Engineers always want to be able to check their results. If we can get the same result using a couple of different approaches, it's a good bet that we haven't made some silly mistake. Since those tend to be embarrassing, always cross-check your results whenever possible. It's a huge waste of time to design a system or calculate a response based on an incorrect equation. So do what you can to check your equations before using or solving them. We've already talked about checking equations before solving them when we use differential equations in the time domain. When we wrote the differential equation, we checked what its response was to a constant input as time went to infinity, even if that wasn't the input that we were actually interested in. The reason for checking the differential equation under these conditions was that we could independently determine what the circuit response should be. Under these conditions, we could replace capacitors with open circuits and inductors with short circuits and analyze the resulting purely resistive circuit. If this response agreed with the differential equation's response to these conditions, we could be pretty sure that the governing equation was correct, and we could go ahead and use it for other analysis or design purposes with a high confidence in the results. It turns out that similar cross-checks are possible in the frequency domain. In particular, we can check our calculated responses as the frequency goes to 0 and infinity against the expected behavior of a simpler circuit. If the frequency domain responses agree with our expectations for these two conditions, we can be pretty sure that the responses are accurate at the other frequencies. To check our frequency domain responses at low and high frequencies, first let's determine the individual circuit component impedances at low and high frequencies. The impedance of a resistor isn't a function of frequency. That means that a resistor is still a resistor, whether the frequency is 0 or infinity. Inductors and capacitors, on the other hand, are a different story. First, I'll look at a capacitor's impedances at low and high frequencies. A capacitor impedance is 1 over j omega c. As the frequency goes to 0, this becomes 1 over 0, which is infinity, and a capacitor has infinite impedance if the frequency is very low. An infinite impedance allows no current to flow, so in this case the capacitor behaves like an open circuit. As the frequency goes to infinity, the capacitor impedance is 1 over infinity, which is 0. Since impedance is the ratio of voltage to current, this means that there's a 0 voltage difference across the capacitor. At very high frequencies, the capacitor looks like a perfect conductor. An inductor's impedance is j omega L. So as omega goes to 0, the inductor's impedance goes to 0. At low frequencies, an inductor behaves like a perfect conductor. As omega goes to infinity, j omega L goes to infinity, and the inductor behaves like an open circuit at high frequencies. This is important, so let's summarize these results. Resistors always look like resistors, regardless of the frequency. Capacitors, however, can be modeled more simply at low and high frequencies. At low frequencies, you can replace a capacitor with an open circuit, and at high frequencies, it can be modeled as a short circuit. Inductors can be modeled as short circuits at low frequencies and open circuits at high frequencies. Next, we'll do an example to see how this helps us check our frequency domain circuit analysis results. This is the RC circuit from a previous video example. The input is V sub s of t and the output is y of t. This is the corresponding frequency domain circuit, and this was the frequency response that we calculated. Now let's use our simplified low and high frequency circuit models to calculate the frequency response at omega equals 0 and infinity. We'll compare those expected results to this equation, also evaluated as omega equals 0 and infinity. If those two approaches match, we can have pretty good confidence in these results. First, the circuit, as omega goes to 0, the input is U at J0. The resistor doesn't care what the frequency is, so its resistance or impedance is 2 ohms regardless of what the frequency is. The capacitor looks like an open circuit at low frequencies. So Y at J0 is equal to U of J0 because there's no current through the resistor and no voltage drop across the resistance. If these two are the same, the frequency response at low frequency is 1. Now let's take a look at this equation evaluated as omega goes to 0. So H of J0 from the equation is equal to 4 over 4 plus 0. So 4 over 4 is just equal to 1. These match and we're in good shape so far. Now let's take a look at high frequencies. For the circuit, as omega goes to infinity, the capacitor looks like a short circuit. So here's my input, U at J infinity. The resistor still looks like a 2 ohm resistor. The capacitor looks like a short circuit, and this is the voltage across a short circuit. The voltage across a short circuit by definition is equal to 0. That means that H at J infinity is equal to 0. From the equation, also as omega goes to infinity, H of J infinity is equal to 4 over 4 plus infinity. Anything over infinity is equal to 0. So this is also 0. The results match at both low and high frequencies, and we can have good confidence in this result. Time domain and frequency domain analyses should also make sense relative to one another. In fact, the frequency domain behavior of inductors and capacitors at low frequencies looks a lot like their behavior in the time domain if the input's constant and we let time go to infinity. This isn't a coincidence. If we calculate steady-state sinusoidal responses and let the frequency go to 0, capacitors behave like open circuits and inductors behave like short circuits. In time domain analysis, if we applied a constant input and let time go to infinity, capacitors could be modeled as open circuits and inductors as short circuits. The capacitor and inductor models for these two sets of conditions are identical. That's because these two sets of conditions are exactly the same. In steady-state sinusoidal analysis, a fundamental assumption is that time goes to infinity. That means that in both of these cases, we're looking for the particular solution. Also, a cosine function with 0 frequency is just a constant. The cosine of 0 is equal to 1, so a number a times the cosine of 0 corresponds to a constant input. Both of these sets of conditions correspond to finding the particular solution to a constant input, so the circuit components had better be modeled the same way in both cases. An important frequency response application is the design of what are called frequency selective circuits or filters. Those are the topic of the next video.